Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to discuss probabilistic models that contain continuous quantities and also discrete quantities. In particular, we're going to discuss how to model the dependence or independence between such quantities. Let's get to it. Those quantities are going to be represented as random variables, so we're going to study the dependence and independence between discrete and continuous random variables. Let's begin with an example. Here we're going to model the temperature at Mauna Loa, this volcano in Hawaii, jointly with the precipitation at this location. And precipitation is going to be discrete because either there's no precipitation or there's precipitation in this very simple model. So we saw in the previous video that a reasonable way to model the joint behavior of precipitation and temperature was to estimate the marginal PMF of precipitation, which tells us the probability that there is precipitation or there's no precipitation, and then also the conditional PDF of the continuous random variable, which is temperature, given the discrete random variable, which is precipitation. So here we have the conditional density of temperature if there's precipitation, that's the solid line, and if there's no precipitation, the dashed line. Notice that when there's precipitation, we have this interesting bimodal behavior where the temperatures are either around here or around here. To me, this suggests that maybe here it's snowing because we're close to 0 degrees Celsius, and here there's just rain, but I'm not sure. Okay, so now something that we should ask ourselves if we're going to manipulate these two random variables together is, can we define the conditional PMF of the discrete random variable given the continuous random variable? This would surely be an interesting object. It would allow us to ask questions such as, what is the conditional probability that there is precipitation given that the temperature is, let's say, 10 degrees? The problem with defining the conditional PMF given this event is that that event has probability 0, because continuous random variables, the probability that they are equal to a specific value is always 0. We already encountered this problem when we define the conditional PDF of a continuous random variable given another continuous random variable. And we're going to address the issue in a very similar way. What we're going to say is, okay, the conditional probability of D being equal to a certain value, given that C is exactly equal to another value, is not well defined, but we can define the conditional probability given that C is in a small interval close to the value that we're interested in. When that interval, the length of that interval shrinks to 0, then the limit of that probability is a meaningful way, like it's a meaningful definition for the conditional PMF of D given C. So that's how you should think about the conditional PMF of D given C. Okay, and this is how we define it, as the limit of the conditional probability that the discrete random variable is equal to a certain value, given that the continuous random variable is in an interval that is shrinking, that shrinks to 0. Okay, that the length of the interval shrinks to 0. All right, so now let's consider, now that we have defined the marginal and conditional PMF and PDF of discrete and continuous random variables given each other, let's talk about how to estimate marginal distributions. So in the case of discrete random variables, estimating marginal distributions is really easy. You have the conditional PMF, you want the marginal over the random variable A. What do? You sum over B. You sum the joint PMF over B. If you have two continuous random variables, A and B, and you want the marginal with respect to A, what do? You integrate with respect to B. Okay, you integrate with respect to B. Now, if you have a discrete and a continuous random variable, in the previous video on discrete and continuous random variables, we saw that if you want the marginal of C, then you can just sum over D. What do you sum? The product of the marginal PMF times the conditional PDF of C given D. Now the question is, can you do the same to obtain the marginal PMF of D? By the same, I mean, can you apply an analogous formula where you integrate with respect, so you want the PMF of the discrete random variable, can you just integrate with respect to the continuous random variable? Okay? Just like we do essentially in the continuous case. What are you going to integrate? Well, you're going to integrate this proxy of the joint distribution, because here we don't have a joint PDF to integrate over. So naively, it would seem that it makes sense to integrate. So here, what is this equal to really? It's by the chain rule, is the marginal of the density of A times the conditional of B given A, right? Here we don't have a joint PDF, but we do have a marginal PDF of C, and we do have a discrete PMF of D given C, which we just defined. So if we just, like by analogy with this, it sounds reasonable to compute the marginal of D by integrating this expression over C. So that's the intuition, how we arrive at this possible formula. Now we're going to show that actually this works. Now I feel that I've annotated too much, so let me clean this up. So this is the question. Is this formula true, which is obtained by analogy with what happens for two discrete random variables, two continuous random variables, and so on? And the answer is that it is true. In order to prove it, we're going to, again, have to do an argument with limits, because we have this conditional PMF that the way we have defined it is as a limit of this conditional probability. What we're going to do is we're going to say, okay, the continuous random variable can be anywhere on the real line. Okay, this is the real line. But we're going to discretize the real line like this. So this would be C minus 1, C minus 2, C0, C1. So are there all these points, okay, that go from C minus infinity to infinity? Basically, they cover the whole real line with a step size of epsilon. So this is epsilon in between. And now what we're going to say is, by the law of total probability, the probability that D is equal to a certain value is equal to the probability that D is equal to that value, and at the same time C is in one of those intervals. Because those intervals cover the whole line, their union basically is the probability of the whole sample space, of this probability space that we're in. So by the law of total probability, again, we have this equality as long as we go from minus infinity to infinity, because we're covering the whole real line. Hopefully that makes sense. But now what are we going to do? Well, we're going to apply, we're going to multiply this by epsilon. When we multiply this by epsilon and divide by epsilon and take the limit where epsilon goes to 0, then this part here, the upper part here, this part here just becomes an integral. Okay, this is how you define the Riemann integral. Okay, you multiply by epsilon, you have this sum, and you take the intervals to 0. So that's where this integral comes from here. And this guy is epsilon, right? Because it's epsilon, epsilon becomes a differential. But we have divided by epsilon, so this is why there's an epsilon appearing here. All right, so this sum that we have defined becomes an integral in the limit, and 1 over epsilon appears. Now what are we going to do? We're going to apply the chain rule. By the chain rule, we get the probability that C is in this interval divided by the length of the interval times this conditional, which is the probability that D is equal to D given that C is in this tiny interval. We have seen that this object, when epsilon goes to 0, is exactly the conditional PMF of D given C. What is this guy over here? By now, this should be familiar. It's a probability that the continuous random variable is in a small interval divided by the length of the interval when that interval goes to 0. That's the density. So what do we obtain? We obtain that the marginal PMF of the discrete random variable can be obtained by integrating the marginal of the continuous random variable times the conditional PMF, integrating all of that over C, over the continuous random variable. Okay, so this establishes that this analogous formula to obtain the marginal PMF also works for discrete and continuous random variables. Now let's take a look at, so now we know how to compute the marginal PMF of a discrete random variable if we know its joint distribution with a continuous random variable. Now let's take a look at the chain rule, which is another important tool when we're manipulating random variables together. So for discrete random variables, we already saw that the joint PMF factorizes into the marginal PMF times the conditional PMF in both possible orders. Same thing for two continuous random variables. The conditional PDF factorizes into the product of the marginal PDF times the conditional PDF in these two possible orders. Now the question is, what about for discrete and continuous random variables? Here we do not have a joint PDF, we do not have a joint PMF, but we do have marginals and conditionals. So the question is it true that the marginal PMF times the conditional PDF is equal to the marginal PDF times the conditional PMF? This is going to be super useful because if this is true, then we have finally a way of computing this guy, which is computing this and then dividing by the marginal density. Okay, but let's not get ahead of ourselves. Let's first establish whether this chain rule for discrete and continuous random variables holds. Okay, so let's do that. What is the marginal PMF times the conditional PDF equal to? Well, we're going to plug in the limit, the definition for the conditional PDF, which is the probability that we're in an interval divided by the length of the interval, and we're conditioning on this event that the discrete random variable has a certain value. Okay, perfect. So now what are we going to do? We're going to basically use the definition. Well, we're going to plug in. So we're going to put the probability into the limit. We can, it's just a constant. And now here, this is just equal to by the chain rule. This is just, so the chain rule for events. Here we have the probability that this equal to D times the conditional of another event given that. It's just this is just equal to the intersection, the probability of the intersection of the two events. Now we can apply the chain rule in the opposite order. So taking out the probability of the random variable, the continuous random variable being in this interval. And now we have the conditional of the discrete random variable being equal to D, conditioned on the random variable, the continuous random variable being in the small interval. Okay, so hopefully that was clear. Because we're taking the limits, now we have probabilities between events, so we can take the chain rule in both directions without any issues. We don't have like a mixture of densities and probabilities. Once we take the limit, we just have probabilities, so it's easy to just essentially apply Bayes' rule if you want here. So now we have this. What happens when we take the limit? What is each of these quantities? This guy is the probability that the continuous random variable is in an interval divided by the length of that interval. It's just the PDF. And what is this guy? This is the probability that the discrete random variable is equal to a certain value given that the continuous random variable is in an interval that is shrinking close to this point C. What is that? By definition is the conditional PMF. All right, so we do have this chain rule for discrete and continuous random variables, which looks essentially the same as the chain rule for discrete random variables and the chain rule for continuous random variables. So now let's go back to Mauna Loa. Remember that we had estimated the conditional PDFs from data, and we also had the marginal PMF. So what if we want to know the conditional probability that there's precipitation given different temperatures? We're going to apply our chain rule. So by the chain rule, we have this proxy of the joint distribution between them. The reason why I say proxy is that here in general is where you would put the joint PMF if we had two discrete random variables, or the joint PDF if you had two continuous random variables, and then would divide by the marginal. Here we don't have any joints, so we put this proxy for the joint, that is the marginal PMF times the conditional PDF, and we divide by the marginal because we know that this multiplied by that by the chain rule is equal to this. Okay, so remember that this guy, by the way, we can obtain by basically just summing this guy up here over D. Maybe I should have written this, but this is from the previous video. Okay, we know how to compute that like that. Okay, so when we do this for the for our example in Mauna Loa, we see that if at low temperatures, the probability of precipitation is actually relatively high, almost reaching, it's higher than 20%. Here, there's this interesting dip here. So then it's quite low at around 5 degrees, and then it's a little bit higher when we approach 10 degrees, because remember that there we saw this bump in the conditional PDF, in the conditional PDF given precipitation, but still most of the time there's no precipitation, and then it's really low again. Okay, so this answers the question of what is the probability of precipitation for different temperatures in Mauna Loa. And the way we compute it is by taking the PMF, multiplying by the conditional PDF, and then we have to divide to make sure that this is a valid conditional PMF. We divide by this sum. So notice that this is just a normalizing, like the marginal PDF, you can almost interpret it as just a normalizing factor so that this guy is a valid PMF, valid conditional PMF. All right, so now let's take a look at another example. In the video on discrete and continuous random variables, we define Gaussian mixture models, where essentially we have a model where we have a continuous random variable h that we want to model. I said model like 20 times, right, in these last two sentences. In this case, it's going to be height. There's like a group of people we want to model their height. And what we're going to do is we're going to have a discrete random variable S, which is in this case represents sex. And in our model, it is the conditional distribution of the continuous random variable given different values of the discrete random variable that is Gaussian. So in this case, the height given a man, given being a man is Gaussian, height given being a woman is Gaussian, all right? But not height in general. So that's why we call this a mixture model, because we're mixing these two populations, and each of them we're assuming is Gaussian, but not the overall population. Okay, so remember, we estimated the PMF. How did we do this? Just empirical PMF of the data. So there's like 1/3 of women's like 1/3 of the population is women. So the PMF is 1/3 and 2/3. Now the conditional distribution of height given woman was computed using maximum likelihood. The parameters were, this was the mean and this was the standard deviation, and it gave a pretty good fit. This is a conditional PDF of the continuous random variable given the discrete random variable. For men, we again applied maximum likelihood. This is the mean, this is the standard deviation, again pretty good fit. For the marginal distribution of age, what did we do? Well, we just sum over the discrete random variable. We discussed this in the previous video, and we get this expression. This is the mixture that I was referring to that allows us to model the whole population as a mixture of these two Gaussian conditionals. Looks pretty good, very good fit. But now we would like to know what is the conditional distribution of the discrete random variable given the continuous random variable. And this is often used for classification. Imagine that you want to classify a person based on their height. So if they're taller, you're probably going to say they're probably a man. If they're shorter, you're probably going to say that they're probably a woman. But how do you quantify this a bit more rigorously? Well, you derive the probability that they are a woman, in this case, given that they have a certain height. Here we're again going to apply the chain rule, where if we want the conditional PMF of the discrete random variable given the continuous random variable, this is going to be equal to the marginal PMF of the discrete random variable times the conditional PDF of the continuous random variable, and we divide by f of h, which is a normalizing factor, so that this guy is a valid conditional PMF. How do we compute it? By summing the conditionals over the two values of the discrete random variable. So when we plug in the formulas, here, this is the probability of being a woman, this is the probability of being a man, and then the rest are the conditionals, okay? So this is the conditional, sorry, maybe I will, so this is, I'm gonna just color code this so that you see this clearly. So those are the discrete, those are the marginal PMFs that we have estimated from data. And then we have the conditional PDFs, which are the rest, okay? This Gaussian variables. This is looking a bit terrible, but hopefully this is just to color code the formula. This doesn't look as nice as I wanted it to look, so let me erase it. How does this look like? Oh, and sorry, like I forgot an extra step. We can actually simplify this by dividing by theta on all sides and also dividing by this. When you do that, you get this expression here, which might remind you of a logistic function, but it's not exactly a logistic function, but I'll get back to this thought. And when we actually look at how this looks like when we plot it with respect to h, okay, this is what the function actually looks like. So it's not exactly logistic because there's this square there, but I'll get back to that. Then as a function of h, this is what the conditional PMF, actually, sorry about that, conditional PMF of sex given height looks like. So just to be clear, for each height, we have the probability of woman and the probability of man, and that this is a PMF, right? We have a conditional PMF for every value of height. It actually looks very reasonable, right? Because for small values of height, the probability of women is very high, probability of man is low. There's a point where it's kind of 50-50 because there is where the two conditionals kind of overlap. And when height is large, then the probability of man is much higher than the probability of women. Again, you might be wondering, this actually looks kind of like a logistic function. Well, you would get a logistic function in a special case where the variance would be the same for the two conditionals. So let's take a look. Let's derive the probability of a discrete random variable given a continuous random variable when you have a Gaussian mixture model where you have two means that are different but the same variance. This is exactly the same formula again that comes from the chain rule of discrete and continuous random variables. Okay, so this is from the chain rule. We have to normalize. Here, down here, just to be clear, we have f of c. Okay, so this really follows directly from the chain rule. Now we plug in the expressions for the Gaussian conditionals, and we're going to do the same trick again where we divide by theta everywhere, and also we divide by this everywhere. And now because the variances are the same, we're going to have some cancellations. Okay, so you can verify that this equal to 1, this equal to 1. Why? Because we're just dividing by this. So when we divide this expression by this, what do we get? We get this 1 minus theta divided by theta because the sigmas cancel out, and we have this square minus this square. And this is where it's really important that the two sigmas are the same, because then we get these cancellations, and now we have an expression here where this is linear in C. So you can see this as a function which is 1 over 1 plus some constant, and then an exponential of minus beta c. And this is exactly a logistic function, which is often used in classification. So you can actually derive the shape of the logistic function used in classification as the conditional PMF of a discrete random variable when you assume a Gaussian mixture model with equal variances. Okay, just so you know. So now we're going to look at another example. We have height and handedness, which basically means if you're right-handed or left-handed. This is the marginal PDF of height. This is actually this is in the same population of US Army. I also know whether people are left or right-handed. This is the conditional PDF of height for left-handed people and right-handed people. They look extremely similar. So what does this suggest about height and handedness? It basically suggests that they're independent, right? If you know that someone is left-handed or right-handed, this is not going to tell you any information about how tall they are. We can do the same thing looking at the conditional PMF. So this is the marginal PMF of handedness. This is the conditional PMF, which is computed applying the chain rule in the same way that we did for temperature and precipitation, and afterwards we did with the Gaussian mixture model for height and sex. And what we see is that it's approximately constant. Notice that towards like here and here, it looks quite noisy. The reason is that if I go back here, there's not a lot of data. So that's why the estimate of the conditional PMF there is quite noisy. You don't have a lot of data there, so it makes it like the probabilities are more unstable. But in general, it looks quite constant. When these conditionals are all exactly the same, then we say that the two random variables are independent. So when a discrete and a continuous random variable are independent, what we mean is that knowing the value of one does not affect our estimate of the uncertainty of the other one. And the way that we capture this mathematically is that the conditional PMF of the discrete random variable given the continuous random variable is just equal to the marginal, or equivalently for any value of the continuous random variable and of the discrete random variable, and also for any values, the conditional PDF is equal to the marginal PDF, like in this example that we saw for handedness and height. We can also define the conditional independence between a discrete random variable and a continuous random variable conditioned on another random variable. The idea is exactly the same. If we know this other random variable A, then information about C, our uncertainty about C does not change when information about D is revealed, or vice versa. How is this captured? It's captured in that the conditional PMF given both random variables is equal to the conditional PMF given just that random variable. Or equivalently, the conditional PDF given the other two random variables is equal to the conditional PDF given just that random variable. So it's exactly the same idea as independence, except that we're conditioning on this third random variable. And that's it. What have we learned? We have learned how to characterize the dependence between discrete and continuous random variables. We have learned how to compute the marginal PMF of a random variable when what we have is the marginal PDF of the continuous random variable and the conditional PMF of the discrete random variable. We have also learned about the chain rule for discrete and continuous random variables, which is crucial when you're doing probabilistic modeling that involves both discrete and continuous random variables. And we have also defined independence for discrete and continuous random variables. And that's all I got. Thank you very much.